Right, good morning everyone and welcome back to the Postgraduate Dynamics course MSD 780. My name is Dewald Hatting and I will be taking you through the last study theme of the Dynamics course where we look at optimization and how we can integrate this with the Dynamics workbench that we've been working with up to now. So before we jump into the optimization algorithm, I'd like to give you a brief review of what we discussed for the dynamic analysis program itself. So the DAP BC workbench is the one that we've been considering up to now. DAP standing for Dynamic Analysis Program and BC just referring to the formulation that we're using, which is the body coordinate formulation. So the body coordinate formulation is quite useful and has quite a few advantages compared to the joint coordinate and the point coordinate formulations, especially in the numerical field, simply because it generates quite a large number of numerical equations that it can then solve computationally. Another thing, of course, is that we don't need free body diagrams. The analysis is purely governed by numerical methods, which makes it an ideal approach within the computational environment. So another important thing is that it is also a general purpose approach, which means we can evaluate a very large number of mechanisms, complex multi-body systems, whether it be closed form parallel mechanisms or serial manipulators such as a serial robot or something like that. So the numerical approach also gives us direct access to the function scripts and the numeric procedures. And since we're not limited by a user interface, we can easily extend this workbench to be integrated with other optimization algorithms or in general other algorithms that we might want to use in tandem with this DAP BC workbench. So with that being said, we can then focus specifically on the optimization algorithm and how we actually want to extend that to the DAP BC workbench. So for the case of the MSD 780 module, we're going to look at the dynamic queue optimizer. So this is an extension of the leapfrog optimizer with constraints algorithm that was developed in the early 2000s by Professor Snyman and also Dr. Alex Hay. They basically gave us a general definition of or a formulation of the optimization problem, which we will be looking at in just a moment. So first we can consider a few advantages and disadvantages of this system. So of course, the dynamic queue and the alpha-psi algorithm being gradient-based approaches, it typically deals with your function derivatives to obtain the minima in the data. So we don't really need a lot of inputs either. We have quite simplified Hessian matrices as well, which means we don't need to worry about that. We basically just need to give it objective function constraints in basic tolerances, and we also need to consider the gradients for each of these objective functions and constraints. So these methods are also extremely efficient, and this applies for any gradient-based approach. So they're quite efficient for complex engineering problems where multiple function evaluations are required. It provides quite a simple approach to dealing with any boundary conditions as well, since boundary conditions are simply linearized constraints. The dynamic queue optimizer deals with this in a very efficient way. And it's also more applicable to problems where many design variables are present. So typically if we have something like 4, 5, or even more design variables, this is quite an efficient problem formulation that we can use. If we compare it to something like a global optimization technique where you have genetic algorithms and they can become quite tedious to solve, take quite long. So to sort of minimize the computational cost, we can rather opt for a gradient-based optimizer and just be a bit more mindful of where we place our starting point. So some of the disadvantages is that it is less feasible for problems where you have quite noisy data or data spikes in your output. And this is simply because it is driven by a gradient-based approach. So ideally you want smooth curvatures whenever you're calculating these gradients. The initial variables also have a significant impact on the convergence behavior. Like we said, we need to be mindful of the starting points. The system is more likely to actually converge on a local minimum rather than the global optimum. So depending on where we place our initial variables or our starting points, it will have an impact on whether it's going to converge to a local minimum or the global minimum. Right, so with that being said, the general definition, we can now look at that. And this was actually formulated by Professor Snyman and Hay back in 2001. And it basically deals with the minimization of some sort of an objective function that is subject to a list of design variables. And it also is subjected to a set of inequality constraints that we define as g, j tilde, which is a function of x, and these values should be smaller than or equal to 0. So some sort of a relation between the design variables that has to be smaller than or equal to some bound. Then we also have a set of equality constraints, which is hk tilde, function of the design variables, and whatever that relation is, it should be equal to 0 at the end. And then we also look at our lower and upper bounds, which are now treated differently from general inequality constraints, mainly because they're linearized. So this just refers to the set of lower and upper boundary conditions that also have to be smaller than or equal to 0. And then finally, we consider this g delta x, which has to do with the step limit. So the limit that we impose between two consecutive iterations on the design variables. So the move limit we can specify in the code that we're going to look at. Typically, it's not very sensitive to change. It should just be within the same order of magnitude of our maximum variable range. Right, so with all of that being said, we now can conclude that dynamic queue is quite a reasonable first order approach to optimization. We do expect our data to be quite smooth for the methods that are imposed either from a forward or inverse dynamics approach. So the dynamic queue optimizer, which favors smooth curvatures, will be quite a reasonable and a feasible approach to the problems that we're going to look at for the remainder of this course. Right, so with that being said, we can now jump in and look at a few optimization only examples. So we're only going to focus on the dynamic queue optimizer and sort of get comfortable with that before we look at the extension of dynamic queue into the DAP-PC workbench. So before we do that, we can first consider this general procedure and the guide to the dynamic queue that was also compiled by Dr. Alex Hay back in 2002, and this is basically an addendum to the code that he made available. So just to give you the summary of what he discusses in his procedure, we first define the objective function under the fch.m script file. Then we define the constraint functions also under fch.m. And then we can go and look at the gradients of the objective function, which we can either define explicitly in terms of the design variables, or we can use some sort of a finite difference approach. Typically, we favor the forward difference method, but you can also apply something like the central difference method. So this is discussed over here as well. Then we also define the starting point or vector x0. We define the convergence tolerances and limits as well. And then we can use the dynamic queue or the dinq.m file to perform the optimization. So this is the command that we will use to execute the optimization on the study. Right, so just to show you what the document looks like. So if we zoom in over here, you will see that it gives you a breakdown of how you have to define all of these things. We will go through this in the examples as well. A few things to just take note of is the boundary conditions or the side constraints that we define differently from the inequality constraints. So we have some sort of a lower and an upper vector that we define over here. So for example, if the side constraints on x1 should be 15, so this is basically the upper bound, then we simply define in the first column the variable that we're working with, which is x1, and its upper bound should be 15. So this says that x1 should be smaller than or equal to 15. x2 has both a lower and an upper bound, so in our lower vector over here, we're just going to put 2 for the design variable index, and then we define 1 over here in our upper boundary conditions. We define 2 in the first column and 10 in the second column, which is then the upper boundary value. And then we can also follow the same rules for x3 and x4. Right, then if we want to execute the optimization, we simply type in xf, so x will be the final or the optimized set of design variables, and then f will be your final objective function value as well. Then we use dinq as our command. We first give it the starting value for our design variables in, then the lower boundary condition, the upper boundary condition, this being our move limit that we discussed previously, and then the tolerances, the convergence tolerances actually on the design variable norms, the objective function norms, and then also on the inequality constraints. And then we have the number of inequality and equality constraints that we define, and k loop is simply the maximum number of iterations. So if the system is not capable of reaching the tolerance on either xtol, ftol, or clim, it will simply go up to the maximum number of iterations, and it will terminate based on the maximum number of iterations instead of on the step size or the objective function, something like that. So over here, they basically just give a breakdown of what we just said. The important thing to notice is that if you were to leave some of these values open, then the default values will be assigned. So things like the number of inequality or equality constraints are optional. If you do not specify that, these values can be determined at the expense of an extra function evaluation that will be performed. So of course, if you, for example, want to specify over here your move limit, but you don't have any lower or upper bounds, you just leave those as 2 open lists. So you start with x0, which is your starting point, 2 open lists, and then you can define your move limit DML, which in this case is set equal to 5. Right, so then the plotting and the optimization histories is also something that we will be considering in the examples. So these will be plotted automatically, and you can actually monitor the change in the objective function for each of the iterations. So you can just change this PRN constant equal to 0 equal to 1, and that will plot it. So this is already changed equal to 1 in the code that you have available, so it should plot this automatically after the optimization has been performed. Right, so jumping back to our mind map, we can now start looking at a few example problems and basically apply what we've just said under the general procedure. So starting with a relatively simple example, we can look at example problem 1. And this considers a single variable function with more than one local minimum. So as you can see here, we just define f of x equal to x to the fourth minus 5x cubed minus 2x squared plus 10x plus 5. And as you can see, we have 2 local minima over here, which we just plotted using the fsolve function in Octave. Right, so with that, we also define it then as a quartic polynomial. The function is analytically known, which means we can actually go and find the gradient and the gradient vector analytically as well. And we assume there are no constraints or boundary conditions that we want to specify on this problem. So we simply want to start with some sort of initial condition or initial value for our x, and we want to see where is it going to converge to, where is it going to give us the minimum. So for that, we consider 2 cases. We first consider the case where we start with an x value of minus 1.5. So if we look over here, this is basically what we expect to get from the objective function. So I'm just going to jump over to our Octave program. We can just clear all over here. And then we can open up, so you'll see under the DAP BC Dynamic Q Hybrid Workbench, if I go one out, this is basically what you'll see in the main folder. We're going to jump right into the Dynamic Q subfolder, and we're going to work with these files over here. So firstly, we just want to start off with the fch.m file over here. And we're going to define our objective function first. So it's a single variable objective function with more than one minimum, like we said. Just to zoom in a bit, we now see that f is basically defined as we had it on that graph back in the mind map. Right, so f is defined. We know that there are no inequality or equality constraints. So this is where these last 6 lines or so come in. They basically just say if no inequality or equality constraints exist, just make it an open list. Right, so then moving over to grad FCH, we only have to find the gradient vector based on the objective function since we don't have any inequality or equality constraints. Right, so this is basically what we did over here. So if we go back to FCH, so if we take the gradient of this, so basically df dx, this basically just becomes 4x cubed minus 15x squared minus 4x plus 10. If we go to our gradient vector, we can see that that is exactly what we have over here. So that means that our gradients have now been analytically defined as well. Right, so then we can jump over to the optim.m file that we have over here. And what I did over here is I defined the two starting points. So I'm just going to switch between this one and the top one, which is then minus 1.5, which is our first case that we're looking at. So just another hint is if you want to uncomment or recomment some line of code, to comment it out, you can just type Control R, and then to uncomment it, it's Control Shift R. Right, so now defining x naught as minus 1.5, we can run x f equal to din q, so we give it the starting points in. We don't have any lower or upper bounds. We assume that our move limit can be default equal to 1, so that's fine. And then we also have 10 to the power of minus 4, which is the norm that we specified on our design variables. And then ftol is 10 to the power of minus 8, which is the default. And then we also have the other default values that we're also going to assume over here. At the end, we just want to say that our maximum number of iterations should be 15. It shouldn't take more than 15 iterations to execute. So then we can head over to our command window and we simply type in optim. And as we can see, it ran quite quickly. So it terminated after 6 iterations based on the function value and the step size. So this value is clearly lower than 10 to the power of minus 4, and this value is smaller than 10 to the power of minus 8. And at the end, our x1 or our design variable value is minus 8.54 times 10 to the power of minus 1, or simply minus 0.8535. If we look at our final objective function value as well, that is minus 1.3526. And we can go and verify this for our analytical equation. So if we go back up, we can see that minus 0.8535 sits around here somewhere. And the value of the objective function is around minus 1. What we got over here, minus 1.35 as well. So clearly it now converged to this point that we have over here. So you will notice that because we defined our starting point around here at minus 1.5, it actually converged at the local minimum and not at the global minimum that we have over here. Right, so we can once again just look at the objective function history as well. We can see there is a clear decrease in the objective function values. So it starts off quite large and then it ends over here at minus 1.35. And we can see that iterations 3 to 6, all of them have more or less the same value for the objective function, which shows that we have some sort of a convergence over here. And for the variable history, we have the same case. Around iteration 4 over here, we can see that the value of x1 sort of plateaued and it converged to the solution that we have of minus 0.8535. Right, so then we now know what the optimized solution is. We said that it converged at the local minimum. So let's now investigate what happens when we change our starting point to the value of 2. Right, so we can once again go back to our Octave. We can simply type in clear all, close all, and CLC just to clear all of the outputs. And then we can head back to our optim.m. Since the problem stayed the same, we only want to change the starting point. We can now comment this out with Control R, and we can uncomment this with Control Shift R. And we just run it again. Right, so once again it converged after 6 iterations, but now the value is minus 51.774 for the minimized objective function value. It once again terminated on the function value and on the step size. And we can now see that x1 is now also different. It's now at 3.84. So not the minus 0.8535 that we looked at previously. Right, so with these we can now go back to our graph, and we can see because we started it at around 2, our starting variable value, it actually converged to the global minimum now. And this value is indeed at around minus 51, and we can see that the converged variable value is also at around 3.84 that we have over here. Right, so clearly this example shows us that whatever we choose for our starting point is going to have an effect on whether it's going to converge to the local minimum or the global minimum. So whenever we do these kind of optimization problems, we do need to be mindful of where we choose our starting point, since this will govern the gradients, and the gradients will govern the basically the direction that it will follow to the either local or the global minimum. Right, so now we can also look at example problem 2, which is a bit more complex in the sense that we now have 2 variables that we are considering. So we just define x1 as x and x2 as y, and then we simply say f of xy is equal to y sine x minus x cosine y. So it's once again an analytically known function. So we can find all of our gradients and all of our objective functions using analytical equations, and we can also validate the solution that we get from a graphical perspective, albeit much more difficult to now find where the local and the global minima sit compared to the first solution that we looked at, or the first problem rather. So with that, we can now define 2 starting points as well, x1, x2, which is minus 3.5 and 6. So x1 is minus 3.5 and x2 is 6. Right, so before we look at that, we can just head back to our code. We can once again type in clear all, close all, and we can head back to fch.m. So you'll see example problem 2. I've already populated the fch file with the equation that we're using. So f is equal to x2 times sine x1 minus x1 times cosine x2 is the one that we're considering. Right, so once again, we don't consider any boundary conditions or any constraints on this problem. We simply want to see where the system will converge if we use that set of starting points. So of course our gradient will only be based on the objective function. However, now we need to derive our objective function in terms of x1 and x2. So gf1 is basically df over dx1, and gf2 is equal to df over dx2. Right, so if we head over here, back to fch, sorry, we can then say, so df over dx1 means that this is a constant, so it's just going to be x2 cosine x1 minus cosine x2. So that is indeed what we have over here. And then for df over dx2, we can say that this is a constant, so sine x1 minus x1 times, so this cosine x2 is going to be minus sine x2, so it becomes plus x1 sine x2. Right, and that is exactly what we have over here. So our gradients are now verified, and we also have our analytically defined objective function. So we can simply head over to optim.m, and we can now comment out everything under example 1, and we can move on to example 2 over here. So we've defined our starting points over here as minus 3.5 and 6, and we simply execute this din queue with all of the relevant inputs as well. So we've just increased our maximum number of iterations to 30, since we expect that it might take a bit longer to converge based on the complexity of the problem. Right, so then in the command window, we just type optim again, and we can see that it now converged after 18 iterations with the value of minus 11.4 on the objective function. Then we can also see that for the x-norm and RFD, once again, both of them at the last iteration are smaller than the tolerances that we specified, so they terminated on both the function value and the step size. And then our final optimized variables as well are minus 1.65 and 10.1. So this being x, this being y over here. Right, so then we can also look at x and f. So x is simply just a reiteration of what we have over here, and f is once again what we have over here. So this minus 11.357. Right, so if we look back over here as well, so the objective function history that we can consider, we see that after around 12 or so iterations, so 12 to 18 iterations, the objective function converged, and it stays more or less constant. And we can also see similar results over here from iteration 15 to 18 for x1 and x2, where they stay more or less constant. Right, so this is simply the optimized solution that we give over here. So what we noticed over here between example problem 1 and example problem 2 is that by increasing the complexity of the problem, you do expect the system to run a bit longer or use more iterations to solve the problem. So the dynamic queue optimizer is definitely dependent on the dimensionality of the problem and also the complexity of the prescribed objective function. So we need to be mindful of something like this as well whenever we're going to integrate now the dynamic queue optimizer into the DAP-BC workbench. Since the DAP-BC workbench is driven by numerical methods and iterative methods, we do expect that the dynamic queue optimizer's solution time is going to be greatly underpinned by the complexity of these dynamic analyses that need to be performed. Right, so the last problem that we can then look at is example problem 3. And this one is a bit more complex in the sense that we now have an inequality constraint as well as an equality constraint. Our objective function and actually all of our constraints are also subject to a set of 4 variables. So this now becomes extremely difficult to verify from a graphical perspective, since we are typically limited to 3D plots, and we don't really have a graphical output for a 4 variable case that we're looking at. Alright, so considering this, we minimize our objective function subject to an inequality constraint and also an equality constraint. But our objective function gradients now need to be considered in their formulative form. So df over dx, like we said, it's basically just the objective function with respect to x1, x2, x3 as you move down the rows. The gradient vectors with regards to your inequality constraints basically says that dc over dx is equal to dc1 over dx1, dc1 over dx2. So across the columns, the constraint remains the same and the variable number changes. Across the rows, the constraint number changes, but the variable remains the same. So we do need to remember this as well. Right, and then simply your equality constraints are a copy of the form that you have for your inequality constraint. It's just now you're working with dH instead of dC. Right, and then lastly, your boundary conditions. So these boundary conditions were defined in the example problem that Dr. Alex Hay discussed. So this is actually this problem that we have over here is one of the standard problems that he defined in his code. So we're going to look at that in a moment. So this is just x1 that should be smaller than or equal to 1. So we do have a lower boundary condition on all 4 of our design variables. And then we also have the upper boundary condition on all 4 of the design variables that we will also need to implement. Right, so for our starting points, we can then use the suggested starting points of x1 to x4, which is then 1, 5, 5, 1. And we can execute this code in the Octave system. So we once again just clear our outputs. And we can recomment this and uncomment this code that we will be discussing in just a moment. So moving over to fch.m, example problem 2, we can now recomment and uncomment this example HOC71. And these things have already been defined in accordance with what we had in the mind map. So for grad FCH as well, I'm not going to run through all of these gradients or how we found it. You're more than welcome to do this as an exercise and make sure that all of these gradients are verified. But this basically just iterates what we said for those equations in the mind map. Right, so since we are working with an analytical equation, all of the constraints and the objective function are analytically known. The gradients are also analytically known. For our optimization or optim.m file that we're looking at, x0 is initiated or initialized as 1551. Our lower bounds are for x1 to x4. All of them are 1. And then for the upper boundary condition as well, for design variables 1 to 4, all of them should be 5. And we can execute the code with all of the other default inputs. Right, so we head over to our command window, type in optim, and we can now see that since we are working with more complex relations over here, it took significantly longer than it did with our first 2 example problems. We can see that it still terminated after 6 iterations, but now it's only based on the step size. The RFD or the convergence tolerance that we specified on the objective function value was 10 to the power of minus 8, so this one is slightly larger than that. Hence it didn't converge on this value. Then if we look at x1, x2, x3, and x4, we can see that each of their design variable values are 1, 4.74, 3.82, and 1.38. And what we also see now, since we do have inequality constraints, equality constraints, and these lower and upper boundary conditions, the system also prints out all of these values. So ideally you want all of these values to either be equal to 0 or to be smaller than 0. So that ensures that all of the constraint function values are satisfied based on the final optimized solution. So what I did over here is you'll see that it didn't print out x and f, and that is simply because I left in the semicolon at the end. So you can now also go and simply type in x and it will give you the values, f, which is then 17.014 at the end. If you want more significant digits, you can simply type in format long, and that will give you the expanded values as well. Right, so that basically takes care of all of the numerical outputs, the objective function histories, which are also plotted. So you'll see they figure 1 through to figure 6 on my screen are the histories of each of the parameters that we're considering. So we can first look at the objective function history, and we can see that it has quite good convergence behavior, especially from iterations 3 to 6. The variable history as well, we can see that at around iteration 4 to 6, these values are essentially the same. And it's basically just continued up until the convergence tolerance is reached. Right, so for the optimized solution, we can then just group all of our design variables together. So x1 to x4, the optimized values are given over here. So this problem basically dealt with if we use the analytical gradient to perform the analysis, the optimization analysis. Now, one question that we might have is what will the effect be if we simply use a forward difference or some sort of a finite difference method to solve this problem? So what I've done is under grad FCH, if we just comment out the analytical values, then we can head down, and over here you'll see there are two finite difference methods that I've added. So actually the forward difference method was added initially by Dr. Alex Hay, and the central difference method was added at a later stage by myself with regards to now finding a more accurate gradient-based approach. So for the problems that we are considering, because we have such a small step size, so you'll see over here delt x is equal to 1.d minus 8, so this is just basically 10 to the power of minus 8. Because we have such a small step size, it isn't really feasible to use something like a central difference method, simply because the central difference method requires an additional function evaluation to perform this gradient difference method. So instead we can just go with the forward difference method, and this should be fine for the problems that we are looking at in this module. And as you'll see over here, it basically just calculates the objective function and constraint values for the given design variable values. And then it also calculates the step values. So this is basically just for dx, and it uses that to perform the forward difference method. So this delt x, you're more than welcome to play around with that as well. Typically 10 to the power of minus 7 to 10 to the power of minus 9 is where we use our values to perform these gradients. We don't want to go too small, otherwise we run the risk of working with machine precision values, which we don't really want. And if we go too coarse, then it also compromises the gradient, and the system is going to struggle to reach a minimum within very small localized minima values. Right, so instead of now using the analytical gradients, we're going to use the forward difference method. So we can just save this, and all of the other things remain the same, so we can just execute optim. Right, and you'll see that we essentially get exactly the same outputs as we did. There are small differences between your X norm and RFD values at the end compared to your analytical values, but overall we can still see that most of these values are either less than or equal to 0. Right, so this also points out an important point with regards to the gradients, is that if the gradients are quite complex to calculate analytically, we can simply use something like the forward difference method. Additionally, we typically don't have analytical equations available for our objective function or our inequality constraints. So instead, we will have to rely on the forward difference method, and this will become quite clear once we've integrated the DAP-BC and the dynamic Q optimizer with one another. So remember that the DAP-BC workbench is an iterative workbench, so we don't have any analytical equations available. Instead, we're going to rely on some sort of a finite difference method to obtain our gradients and also our objective function and inequality constraints, and equality constraints as well. Right, so with that being said, we then can basically conclude on what we've seen with regards to all of these optimization-only examples. So we saw that the dynamic Q optimizer is quite powerful since it is a gradient-based optimization method, and it is ideal for function analyses where we have some sort of a smooth curvature and we don't have any noisy data or spikes in our data. The computational efficiency, of course, depends strongly on the choice of initial conditions that we use, the number of design variables or the dimensionality of the problem, and the complexity of the function evaluations themselves. And then with regards to the dynamic Q optimizer being a gradient-based approach, we do need to take care with where we specify our initial design or our starting points or starting vectors, since it is susceptible to converging to a local optimum rather than the global minimum. Right, so with all of that being said, we can then also look at the extension of dynamic Q to the DAP-BC workbench. So we're going to focus on the numerical changes in the next lecture. For this lecture, we can just consider a few important points of why we want to do this and what are the limitations of the dynamic Q optimizer within the DAP-BC if we were going to integrate it. So in this lecture, we now considered easily verifiable analytical functions. However, we know that the real-world problems and the dynamic analysis that we're going to perform will most likely not have an analytical representation. So DAP-BC and the dynamic analyses that we perform in that workbench is an example of such a case where analytical equations are not available. So in these cases, the dynamic properties are calculated using an iterative integration technique. You might recall from the code that DAP uses ODE45, which is the Runge-Kutta integration scheme, which is an iterative method. It also uses complex function evaluations. Noisy data may definitely be present, and the gradients can only be determined through finite difference methods. So a few examples that we consider is something like varying the length of a rotational acceleration of the driven pendulum to minimize the moment, minimizing the acceleration of a tire subject to its stiffness and free length and its other dynamic properties, minimizing the torque on the body of a cart by optimizing the wheel size or the aerodynamic properties, maximizing the speed of a conveyor belt subject to friction model parameters. So remember, we can do both minimization and maximization problems using optimizations. To do a maximization problem, we simply take our objective function and we multiply it by -1. So then our maximization problem becomes a minimization problem. And lastly, we can also consider something like determining the contact model parameters that will ensure that the acceleration of a falling rod is also optimized. So these are some of the example problems that we can consider for the dynamic Q DAP-BC hybrid workbench. And we will be discussing these things in detail in the upcoming lectures. So for this lecture, we only focused on the dynamic Q optimization in its isolated form. For the next lecture, we will now be looking at how we're going to integrate this into DAP-BC. So thank you very much, and I'll see you in lecture 13.